Okay, good evening again, everyone. Welcome to session number 2 of the amateur radio technician class. First of all, I'd like to thank everyone for their comments and questions that was sent via email from the last session or session number 1. Just to recap what we did last session, we had a look at talked a bit about React as an organization, the structure of React, what amateur radio is, the classes of amateur radio licenses, the material that has been distributed for participants to study. We looked at the exams, the various exams for the 3 levels, technician, general, extra. We talked about the website links to the practice exams, which we highly recommend that persons consider. And we went a bit into the technical material, and we ended up at the point where we had discussed Ohm's law. Now, I did promise you an easy way to remember Ohm's law. So we pick up from where we left off, and let me see if I can fulfill that promise by providing what I learned in school way back when. This simple diagram, we refer to it as a mouse plate, and that is simply because Harry Amau was my physics teacher in high school, and he introduced us to this simple representation, a graphical way of remembering Ohm's law, hence the reason we call it a mouse plate. So if you recall from our session, the text, it said that there was an equation or a relationship between 3 things that we talked about during our introductory session. We talked about electromotive force, or EMF, that's measured in volts. Sometimes we call it voltage. We talked about current, which is measured in amperes, the symbol of which is I. And we talked about resistance, which is measured in ohms. The symbol, of course, we use R. So those 3 things we discussed a bit. We talked a bit about the theory, and then we went straight into the questions on the tests that's associated with these terms. But in studying, sometimes it's helpful for us to have some aids to memoir. So we have this a mouse plate that you see the 3 terms that we discussed represented there. E, meaning the EMF or voltage, I, the current, R, the resistance. And we have the main formula here. E is equal to I multiplied by R, or E is equal to IR. We also said that we can derive the other formulas, that if we knew 2 things, we could calculate the other by manipulating using algebra to solve for the other term. So if we know E is equal to I multiplied by R, we could solve the others. I is equal to E divided by R, or E over R. R is equal to E divided by I, or E over I. But this a mouse plate that you see here is a way, if you, and you can do it in an exam, you could do it when you're studying. You create the plate by putting a little line across the circle, a line from the center of the circle downwards, so forming a sort of a T within a circle, and then you have the 3 terms, E, I, R, almost in alphabetical order. And why a mouse plate helps us is that if we want to find any one of these formulae, or the formula that says E is equal to something, we can look at the plate and say, okay, I want to find out what E is equal to. Once I've laid out EIR in this way, I can say, without using algebra, I can use a visual representation here. So maybe I'm not too up and up with algebra and I don't find myself needing to do the manipulation. I can use this for now to help learn and memorize the formula. So let's take a look at it a little further. If I want to solve for E, which is voltage, remember, I say E is equal to the rest of the terms. What are the rest of the terms? I, R. And when we have two terms side by side, we understand that we mean multiply or multiplication. That's why with the equation, when we say E is equal to I multiplied by R, sometimes we shorten it to say E is equal to IR. Sometimes people put a little dot in the middle to mean multiply. Sometimes they leave it out, or sometimes they put the multiplication sign. But however you put it, it means the two terms are multiplied by each other. So if we look at a mouse plate here, we see E, and we say equal to the other two terms. Well, what are the other two terms? I side by side with R. So it must mean E is equal to I multiplied by R. So just to illustrate the use of the plate to find the other two terms, current and resistance, let's solve for I. Let's find out if we had, we wanted to find out what I is equal to. What do we do? Well, we are solving for I here. So I is equal to the other terms. What are the other terms? I is equal to, we move across here and see it's E, and then we see the E is on top of the R. So we know that it's E divided by R, or E over R. So looking back at it, we can see that I is equal to E over R. Now, you probably already figured out by what we have just done that we can also solve for what R is equal to using a mouse plate. In the same way we solved for I, we look at it and say, okay, R is the term that we want to solve for. We want to find out resistance equals to what? So again, we use a mouse plate. R is equal to the rest of the terms. So R is equal to E. It's physically over the I. So we conclude that R is equal to E over I, or we say R is equal to E divided by R. When you have two terms, one over the other, it means the top term gets divided by the bottom term, or the numerator and the denominator. You take the denominator and the numerator together, divide, and you get a result. So R is equal to E over I. So if we go over these three formulae again, we see E is equal to I multiplied by R. I is equal to E divided by R, and R is equal to E divided by I, which are the three formulae that we see represented here, which we discussed in the last class. So I did promise you a special feature today at the start, a way to remember to learn Ohm's law formula. So if this helps you, then adopt it. If it's not necessary to be used, that's okay as well. But this is a way that we can learn and use Ohm's law. So if you're going to do any Ohm's law calculation, maybe the first thing you could do is draw a circle, draw a line through the circle, and draw a line from the middle of that line to the bottom of the circle. So you have a little, pie divided into three places. And put the E on top, I next, R. And then now, when you have to do a formula to find out what the formula is, you simply look at a mouse plate. So there you go. So moving right along, we are going to go into the material, pick up where we left off. So let's go straight into the material. Just give me 1 second to bring up the material. And I trust and hope that you have been able to access the PDFs that were sent via email to you. No one has indicated any issues, so I trust that you are able to access it successfully. Yes, thank you very much for your comment, Eric. Right. There we go. This is where we picked up, this is where we left off last class, where we dealt with Ohm's law. And we did say hams obey Ohm's law. So very important that we get this, because we would need to calculate some values. And we also have a couple other formulae coming up, like power equals something and so on. So we stopped here where we derived from Ohm's law, current is equal to E divided by R, or E or I is equal to E over R. So let's continue. We did talk about a couple examples last class, but let's go into the examples as it applies to the course and to the question pool. Just a comment here. Anyone who is in the class that might have missed first session, I encourage you to play the recording back, because there are some concepts that apply to all of the classes. And we would like to recommend that each person looks over that bit of information, as it can help you understand the further classes, right? So in there, you will see that we talk about this course being exam focused, which means that we are lightly touching the theory, but we are going straight at the questions that you will encounter in the question pool and in your exam. Hence the reason we say it's exam focused. And the reason we do this is to hopefully everyone will gain a bit of an understanding about the theory and be able to apply the theory, so that we don't just learn off a series of questions and what the answers are, the correct answers and the wrong answers. The approach we are taking is look at the theory a little bit and then go straight to the questions. So let's do just that. A question on Ohm's law that comes up is, what is the resistance of a circuit in which the current of 3 amperes flows through a resistor connected to 90 volts? So before we answer this question, let's go back up and remind ourselves what is a circuit. This is what we did last class. We talked about an electrical or electric circuit. And we talked about it by using water, or water circuit as the analogy. We said we have a battery, which in the water system you could consider to be a pump. We talked about a resistor, which in the water circuit might be a shut-off valve or a tap, lock-off valve. And we had the current, which is the flow of the electrons. That's what's flowing in an electric circuit. In a water circuit, is water flowing. But in an electric circuit, you have current, which really represented by electron flow. So electrons are what flow. So this is a circuit. And we see that the battery is connected to a resistor connected back to the battery. So a current flows. The same way if you have a pump and you have your water tank and the pump sends the water through and so on, right? So this is a circuit. So when we're talking about the calculations and they're talking about a resistance of a current flowing what is the voltage, they are really referring to an electric circuit like this one. So back to the question. And we are dealing with Ohm's law. This is the question. I segue a little bit to mention that next to each of these questions, you will see in brackets a term like this, T5D04. That is the question pool number. So the full question pool that you have, if you were to search for this number, you will find the actual question, which is the same as this. But not only will you see what the right answer is, you will also see the distractors, the wrong answers. In our class, we are only looking at the correct answers. So how do we calculate the answer to this question? It tells us we want to find out resistance, R. But we have been given current of 3 amperes, or I. We have also been given the voltage, or E, which is 90 volts. And if we remember from before, if we want to find R, we manipulate the formula, the Ohm's law formula. We end up with R is equal to E divided by I, or R is equal to E over I. And remember a mouse plate, if you have drawn it, you can look at it visually and you can see that R is equal to E, which is on top over I. So all we do, once we have the formula, once we have derived the correct formula, we sure we are using the right formula to do the calculation, all we do is substitute the values in the formula and solve for R. So what are we substituting? The first thing we substitute is E, which is the voltage or the EMF. And the question gave us what the voltage is, 90 volts. So we put 90 where E is. Then we substitute the current, I, and it tells us what I is. 3 amps or 3 amperes. Remember last class we said amperes can be abbreviated by the term amps. So if we put 90 here and we put 3 here, and the formula is R is equal to 90 divided by 3, which is what we get here. Divided 90 by 3, we get 30 ohms. Why ohms? Because the ohm is the unit of resistance, and we are solving for resistance because the question says, what is the resistance? So after we do the calculation, we can't just say 30. It's 30 ohms. And the question pool has that as one of its answers. And we have solved the problem, and we can tick the correct answer. Let's do another example. The other example is very similar. It asks us to solve the resistance. So we already did the work to find out what is the resistance formula above. So we will use that same formula here. The question is, what is the resistance in a circuit for which the applied voltage is 12 volts? Remember, as we read the question, we're picking out things. So we're solving for what? Resistance. It tells us that the voltage is 12 volts, and it goes on to tell us that the current is 1.5 amperes. So you see, they tell us what we want to solve. They give us the other terms, the values relating to the other terms, and all we need to do is plug it into our formula. And what is our formula for resistance? We solved it above. We said resistance is equal to E divided by R. So very quickly, E is voltage, 12 volts. I, the next term in the formula is amperes, 1.5 amps, that's the current. So 12 divided by 1.5, you get 8 ohms. And that's where a calculator comes in handy. We did mention in the first session that you may want to have a simple calculator, probably with very simple scientific functions, such as logarithms. So you need to be able to do divisions and multiplications, or you could work it out otherwise. But a calculator is very handy to have, if only to verify your answer. Let's do one more example to drive the point home. We have done two examples exactly like this. So let's move quickly. Question: what is the resistance of a circuit that draws 4 amperes from a 12-volt source? So notice they're mixing up how they ask the question, but if you realize they're talking about the same circuit, a circuit that has resistance, it has a current flow, and it has a voltage. So guess what? That's Ohm's law. And we have already perfected our knowledge of what Ohm's law is. We know the formula from above. Guess what? It's the same formula we're using again. R is equal to E over I. So all we do, we plug the values into that formula to solve for R. What is E? The voltage, 12 volts. So we plug it in. What is the current? 4 amperes. We plug it in. 12 divided by 4, 3. The answer, 3 ohms. And if we look at the question pool, we'll see 3 ohms is one of the answers. So again, we're only dealing with the correct answers. On your own, you can look at what the distractors are, or the wrong or the incorrect answers. You might get things, A is 3 ohms, B is 30 ohms, C is 33 ohms, D is 12 fours or 48 ohms. You know, they'll give you all kind of numbers inside of there, but you know Ohm's law, you know the relationship, so you're able to properly calculate it. So we're on page 7 of the technician manual. All right, so we're going in a little bit different direction. Before we were solving for resistance, let's do somewhere we solve for current. Question is, what is the current in a circuit with an applied voltage of 120 volts and a resistance of 80 ohms? All right, so they're using some larger numbers. So we might want to bring out the calculator. Yeah. But we are not phased. Why? Because we know Ohm's law. And we know that we can solve for any of these 3 terms. When we manipulate Ohm's law formula and solve for current, we discover I is equal to E divided by R. So we plug in the value for E. E is voltage, 120 volts. So you see, 120 volts. Divided by R, R is what? Resistance, 80 ohms. There goes the 80 ohms. So we divide 120 by 80, and we get 1.5 ohms. Satisfy yourself using a calculator that 120 divided by 80 is 1.5. And there's the answer, 1.5 amps or amperes. Another question like this, they mix it up. What is the current through a 100 ohm resistor connected across 200 volts? Same formula. We're solving for current. So we need the formula of the form that says current is equal to something. So current is equal to voltage divided by resistance. What is the voltage? They tell us 200 volts. We plug it in. What is the resistance? We look for it. 100 ohms. We plug it in the formula. So we end up with a formula that says 200 divided by 100, right? Just always bear in mind 200 volts divided by 100 ohms, right? Equal to 2. 2 what? 2 amps or 2 amperes. Let's do one more. Now, these are real questions that you get in the exam. All right? So it wouldn't be, none of these questions would be a stranger to you once you study the question pool. When you go in that exam and you see those questions, you say, hey, look at that question there again. Nice. What is the current through a 20 ohm resistor connected across 240 volts? Well, what they're asking us, what is the current? So already we know we need a formula that says current equals something. They give us the resistor is 24 ohms. They give us the voltage is 240 volts. We know the formula, I is equal to E over R. We plug it in, 240 divided by 24, 10 amps. Look the answer there. Very well. So let's do the last form of the Ohm's law equation, the way we learned it, where we say voltage is equal to the current by the resistance. So we have some questions like that as well. What is the voltage across a 2 ohm resistor if the current of 0.5 ampere flows? Now remember the same circuit that we looked at earlier we're talking about, right? We have a battery or voltage, we have a resistor, and then the circuit causes current to flow. So don't get tied up by the way they're asking the question. They're all talking about an electric circuit, a simple electric circuit, as we saw earlier and last week. They're just asking us what is the voltage, and they're giving us what is the resistance, and they're giving us the current flow. So again, we come back to the formula. What is the formula? E is equal to IR. You could use a mouse plate as we showed earlier, or from the formula we learned last week. Voltage is equal to the current multiplied by resistance. Simple. So we plug 2 ohms and 0.5 amperes into that equation. Yes? This equation. And what do we get? E is equal to I multiplied by R. E is equal to 0.5 multiplied by 2. Where did we get the 0.5 and the 2? In the question, it says 0.5 amp or 0.5 amperes and 2 ohms. 0.5 multiplied by 2 is 1. 1 what? 1 volt. Because they ask us what is the voltage. So quickly, 2 other examples of the same type of question. They're asking us here, what is the voltage across a 10 ohm resistor if a current of 1 ampere flows through it? Again, they're asking us what is the voltage. They give us the resistor value. They give us the current flow. All we do is use our trusty formula that we have committed to memory. E is equal to IR. And we plug in I and R. I is 1 amp. Look at here. 10 is 10 ohms. Look at here. We multiply 1 by 10. Presto. 10 volts. Which is the answer. All right, so question and answer. Let's do one more before we take a 2-minute break. Again, what is the voltage across our 10 ohm resistor if a current of 2 amperes flows through it? Similar question, right? Well, we ought to have confidence by now because guess what? We are now experts in the Ohm's law formula. And we know E is equal to I multiplied by R. We solving for E, they give us I, and they give us R. We just need to multiply them. 10 ohms, 2 amperes. 10 multiplied by 2, 20 volts. So folks, that is our bit of practice using Ohm's law, using actual questions from the question pool. We utilize the theory about Ohm's law to solve questions. So at this time, we will take a 2-minute break. We'll come back at 4 minutes past 9. So if you wish, get a drink of water, bathroom break, to take a stretch, please do so. And we'll be back with you very shortly. Okay, we'll start back in 1 minute's time. 1 minute time to restart. Okay, welcome back, welcome back, everyone. After that short break, we will continue and discuss series and parallel circuits. So last class, we introduced you to the electric circuit. You remember there was a battery, there was a resistor, and then we said current flowed. But notice in this circuit that we're looking at here, it's a bit different to the one that you saw last class. Where last class we had one resistor, notice now we're seeing two resistors. This is like in the water world having a pump, a tap or lock-off valve here, and another lock-off valve, and it returns into the pump. So the resistors, remember, impedes the flow of electrons, or it impedes current flow, right? So it's just we have two resistors. But of course, there are different ways that you can connect resistors. If we have two of them, the way when you connect one resistor to another, like this, it's called a series. One connects directly to the other, right? So if water is flowing in this circuit, it will flow through this resistor or lock-off valve, and it will also flow through this lock-off valve and return, right? So this is called a series circuit. There's only one path for the current to flow. Notice, one pathway that the current will flow. Yeah? So we say it's the same current that's flowing through everywhere, including the resistors. Same current when you are in series. What we also need to note is, although the current will be the same, it's like water, you know, same current flow. But even though the current flowing is the same across through the two resistors, the voltage, if you measure them across the resistor, might depend on the value of the resistor. In the water circuit, you know, you can have a quarter turn valve and you just turn it a little bit. Or if it's a gate valve, you just open the tap a little bit. But the other one might be fully open. So one presents more resistance to the other, yeah? So the same current will flow through both, but the voltage might be different. Yeah? Simply because one resistor might be higher or lower than the other. In the same way in a water circuit, which is the analogy that we're using for the class, you might open one pipe a little more than the other. Therefore, the one that open less presents a higher resistance than the one that open more. Same thing with resistors. They come in different values. Resistors are components in an electric circuit, just like valves or taps or lock-off valves are in a water circuit. So in a series circuit, the current flowing through is the same, but the voltage at the different components might be different. I say might because they could be the same, depending on if the value of the two resistors are the same. If the value is the same, well, you might get the same voltage. Okay? So let's go to the questions that asks about series and what we just talked about with respect to the currents and the voltage in a series circuit. The question is, in which type of circuit is current the same throughout all components? Well, we just said that in this circuit that is on the screen, we call this a series circuit. We did say that the current flowing is the same. Just like if it's the water circuit, water flowing is the same. So therefore, which type of circuit is current the same throughout all components? That type of circuit is a series circuit. So here is the tie-up kind of question they want to ask you now, right? Look what they're asking you here. What happens to current at the junction of two components in series? Well, look what they're trying to tie up now. They're using some terms, junction. Well, junction is no big deal for us. We know in a roadway, you have a junction. In an electrical circuit, you have a junction box. In a water circuit, you have these places where you clean out and so on, right? That's all that is. A junction is simply a connection, right? But they put it in terms to try to tie us up. But all they're asking us here is what happens to the current when you're in series? And we said that in a series circuit like this, the current that flows is the same. In other words, it doesn't change. And that is the answer. What happens to current at the junction of two components in series? It is unchanged. So don't be fazed by how they try to tie up the question, right? You know that in a series circuit, the current is the same. So they cannot fool you, however they ask you the question. They'll ask you the junction. Well, the junction is where these two things connect. The current is the same. One more other kind of question they will ask you, right? Remember we talked about the resistors could be the same value, just like you have pipes could be open the same amount, or one might be open a little more than the other. This is their question. What is the voltage across each of two components in series with a voltage source? Yeah, that's just a tie-up way of asking you the same question, right? We said that if the resistors are the same, then the voltage would be the same. But if the resistors are different, the voltage across one would be different to the other. So in other words, the voltage is dependent on the values of the resistors. What is the voltage across each of two components in series? And those two components could be the resistors. So you see how they're saying two components? Well, imagine those two components are the resistors in series with a voltage source. The answer is it is determined by the type and value of the components. So the key here is value. The value of resistor 1 and the value of resistor 2 will determine the voltage of these components. So because it's dependent on the resistance of the components, it's determined by the type and value of the components. So a very tie-up way they're trying to ask you, but you know that the voltage depends on the value of the component. We are talking here about resistors. So because we're talking resistors, we're talking resistance. All right. Let's move along. So we talked about a series circuit, and we understood what a series circuit is by saying that a series circuit, the current flows through all of the components. Yeah? In other words, if this were a water circuit, water can't get from here to here without passing through this and this. Resistor 1, R1, and R2. If it were a water circuit. In the same way, an electric circuit, the current cannot get to this point here unless it passes through this component, goes through the wire here, passes through this component, and then ends up on this wire, ends up on this wire, ends up on this wire. So this is a series circuit. But a parallel circuit is different. Notice that in a parallel circuit, we see that there are two branches that the current could take. The current could go this way and end up here at this junction and then flow through this resistor and come back here, return here. So it's going this way. But the current could also take another path and come here on this leg, pass through this resistance, R2, end up on this leg, and return to the battery this way. Just like a roadway, you have an avenue or a main street, and you could, to get back here, you could either pass through this road, or you could go the long way and pass through this road to come back to here. Same way in a circuit. So when we have the option for the current to take another pathway, that is called a parallel circuit. But we notice that the current divides between going here and going here. So whereas in the series circuit, the current is the same throughout, but the voltage is different. It's the opposite with a parallel circuit. Meaning that the current is divided and the current flow is dependent on the value of the resistance, but the voltage is the same. All right? So let's go directly to the question that asks on the concept. In which type of circuit is voltage the same across all components? Well, the last thing we just said was that in a parallel circuit, the voltage is the same. So therefore, the answer is parallel. Yeah? Let's see the other question that they ask. What is the voltage across each of two components in parallel with a voltage source? Well, that's asking the same question in a different way. The answer is the voltage is the same as the source. In a parallel circuit, the voltage is same for this source as it is for this resistor, as it is for this resistor. Voltage is the same. What is different is the current. Okay. All right, let's deal with the last question in this section. What happens to current at the junction of two components in parallel? Again, another technical way of asking what we just discussed. Remember we said in a parallel circuit, the current has two choices here. We have two roadways. You could choose this road and come down here, or you could choose to continue the longer route and come down here. So the current has two ways to go. But the way this thing works is like water. If you have a pipe and you have two ways for the water to go, guess what? The water will flow here and the water will flow here. It will flow in both pipes and come back around here. So the current divides itself. Well, let's look at what the question is. What happens to the current at the junction of two components in parallel? The current divides between them dependent on the value of the components. So the current is going to divide depending on what the value of resistor 1 is and what resistor 2 is, will determine what current actually flows in each of these, right? We don't yet know the values of the components, but when that time comes, we will plug those into a formula and we will be able to calculate current based on a series or parallel circuit. We know the behavior of a series circuit from before, and we know the behavior of a parallel circuit. So that's what we need to contemplate, review, and make sure that we have clear. What's the difference between a parallel circuit from a series circuit? Okay. Let us now look at power. The DC power they're talking about here is simply direct current power. They tell us that power is the rate at which electrical energy is generated. They also tell us that power is measured in watts. Well, we should be familiar with the term watts. If you're going to buy a bulb or a lamp, whether it's the incandescent type or the fluorescent type, you might ask for a 40-watt bulb or a 60-watt bulb or a 100-watt bulb. If you're buying a microwave oven, you'll probably see the ad that say this is a 1100 or 1100 watt microwave oven. And you might see another one next to it saying 900 watts. So we should be already familiar with the term watts as a measure of power. All right? So just recall that power is the rate at which electrical energy is used. So if you have a 60-watt bulb, 60-watt bulb will use more power than a 40-watt bulb. If you have a 1100-watt microwave oven, it will use more power or consume more power than a 900-watt microwave oven. So let's look at the questions associated with it. And we'll just come back to the one question, we'll come back to the unit of power. Simple question, what term describes the rate at which electrical energy is used? Well, we just learned that the term is power. But what W-A-T-T, is the unit of power? We use W as the symbol for watts. All right, so power is measured in watts. Look at the question. Electrical power is measured in which of the following units? So they'll give you 4 choices. You know that the answer is watts. Electrical power is measured in watts. Here's the statement. So anytime you think about electrical power, think about your bulb or your microwave. And you think about what just the same way we'll say, okay, a car is this 50 horsepower, right? Microwave oven or a bulb, 900 watts, 60 watts, measure of power. But like everything else, we have a formula associated with it. So earlier we learned about Ohm's law, we are now going to look at the equation to calculate power. The nice thing about this equation, it is very similar to the Ohm's law equation we just learned. It involves just three terms. The term power and two other terms that we learned about last week that we used in the calculations this week. That is voltage and current. Now notice we leave out resistance. So resistance in the cold with this formula. Not a wrong, no, nowhere. We're only talking voltage and current. So the formula for power is we multiply the voltage by the current to get power. So power is equal to E multiplied by I. Power is the product of voltage by the current. P is equal to E I. And that's the next formula that you need to commit to memory, learn, and become familiar with. Again, fairly simple formula. It's not 20 terms. It's not using a lot of mathematical operations. It's a simple multiplication, multiply. Okay, so now that we have learned the formula for power, P is equal to EI, let us end today's session by going through a couple questions that they will ask you about power, and maybe we'll deal with one calculation before we bring today's session to a close. Okay, so we just learned about power. We just learned about the unit of power called the watt, and we also learned that to calculate power, we simply multiply the voltage by the current. The question: what is the formula used to calculate electrical power in a DC circuit? We just learned that power is equal to the voltage multiplied by current, and that's the answer. Power equals voltage, E, multiplied by current, I. Simple question with a straightforward answer. The key is to learn the formula. P is equal to E multiplied by I. Again, in the question pool, the distractors, they might try to tell you that power is equal to current by resistance or voltage over resistance. From the time you see an answer with power and resistance there, you know, that's not what you learn. What we're talking about, have no resistance in the equation, at least in the simple form that we're learning in it. So you know any answer with resistance will be wrong. So you could cross that off one time, and you're looking for the one that has current and voltage. But careful, don't fall for the trap where they might say power equal voltage divided by current and all kind of thing like that, you know. It's voltage multiplied by current. Those are some of the tricks they will try to pull on you in the question pool distractors. Let's quickly look at a couple of calculations associated with that formula we just learned. P is equal to E multiplied by I. The question is, how much power, that means we're solving for power equals something, how much power is being used in a circuit when the applied voltage is 13.8 volts DC and the current is 10 amperes? Well, we know once they ask us for power, the formula that we're using is what? P is equal to E multiplied by I. So all we have to look for in the question is what is E and what is I. But they give us that. They tell us E, which is the voltage, is what? 13.8. Look at right there in the question. The next thing we're looking for, we have E already. We're looking for the I, the current. Look, they come and tell us current is 10 amperes. So we have the two things that we need. You know, 10 apples at $5 an apple, $50, right? So P is equal to E multiplied by I. We know it's 13.8 volts, 10 amps, 138. But 138 watts? Yes, 138 watts. Because the watt is the unit of power. Let's do another one. how much power is being used in a circuit when the applied voltage is 12 volts DC and the current is 2.5 amperes. Again, we know the formula for power. They're asking us how much power. Well, power is equal to E multiplied by I. So we just look in the question, what is E? Voltage is 12 volts. We look for current, I. Current is 2.5 amperes. We multiply them. P is equal to E multiplied by I. Substituting in the formula, we get 12 volts multiplied by 2.5 amperes. 12 by 2.5 is 30. 30 watts. So they make the point here. Just as with Ohm's law, you can use algebra to come up with the other forms of this equation. Remember, we did algebraic manipulation. We moved the terms around. If we know one, if we want to solve for one, we just need the other two. So to calculate voltage, if you know the power and the current, or to calculate the current if you know the power and the voltage. So we will end there for today, having dealt with the power formula, P is equal to E multiplied by I. So we would ask that persons email any questions that you may have in respect of the material. We will do our best to put up a recording of today's session so that you can review. You have the book, this book that we're using, so I encourage you to read over as well. And I'm using the exact book so that when you look at the material, it will be no different. That's why we're not using slides, we're using the actual PDF text. You can feel free to read ahead. Basically, what we do is we go through the material to occupy 1 hour. So feel free to read ahead and post any questions that you wish via email, and we'll do our best to answer. So our next session is expected to be next week, Friday, which is the 12th, and an email will be sent to you in advance of that date with the link to the Zoom session. Once we have the recording up on YouTube, we will also forward that. So do check your email from time to time, and we will keep in touch. And if there are any issues between now and our next class, I will certainly communicate with you. There were a couple questions and suggestions to change the date and time. We will discuss that a little further to see if we wish to switch the date and time for the sessions. So with that being said, we looked at some Ohm's law calculations today, the various forms of Ohm's law's equation. We introduced you to an easy aid de memoire to the Amau's plate, way of remembering that formula. After the calculations, we discussed power, and we also talked about the difference between a series circuit and a parallel circuit. What happens with voltage and what happens with current in both types of circuit. So thank you again for your attendance, for your kind participation, and also for your feedback. Yes, certainly welcome, Eric. And do take care, everyone. Do have yourself a good rest, a good evening, a good night. Have a great weekend. Be safe, everyone, and be careful, of course, with the weather that we are in the rainy season, and we need to take all necessary precautions. And as REACT, we are prepared for what may come. So be safe, everyone. Thanks again. Have a good night.